Yeah, I'm really happy to be here. So my name is Tobias. I work at CERN. I'm a doctoral student at TUM. And together with Brendan Keith, Boyan Lazarov, Stochastic PDEs, and Barbara Wohlmuth, I've been working on the following problem. So solving stochastic fractional PDEs with MFEM, with applications to random field generation and topology optimization. So what we want to do in this talk is we want to generate random fields, and we would like to apply them in the context of topology optimization. In order to get there, we have to solve a stochastic fractional PDE. But right now, for the beginning, the most important thing for you is to understand what a random field actually is. All right, this is a random field. So you can see that it has seemingly random values distributed all over the domain, but it does have a specific spatial structure. In mathematical terms, we call this specific spatial structure, we call it covariance. So for this talk, we're going to restrict us to so-called Gaussian random fields. And a Gaussian random field can be characterized by two properties and two properties only. These two properties are its mean and its covariance. But right now, we don't want to go very deep into the theory for random fields, but we would like to give some examples from applications. So for instance, random fields are an essential tool for the geostatistical community. So what you can see in this work is that researchers evaluated the effectiveness of malaria prevention mechanisms. So in the values that you can see on the map of Africa, they come from a combination of a regression technique and random fields. I suppose the majority of you is not coming from that community. I suppose the majority of you is rather an engineer, maybe mathematician or a physicist. No offense if I didn't name your discipline here, sorry. So what might be more interesting for you might be the following application. So this is work from Prishenko and co-workers. So they superimposed a random field on top of some base topology, like an octet truss or a guroid. And what they can do then is they generate those random imperfections with the random fields, and then they have these random imperfections that model the uncertainties of the manufacturing process, and they can then evaluate certain quantities of interest, like I don't know, they can evaluate stresses on it, and this allows them to analyze the real thing that you get out of the additive manufacturing process. Another application I like a lot is from Brendan Keith, one of the people that you've also seen on the front slide. So in this case, they have a specific random field that obeys the same physics as the actual airstream. So they use this random field that you can see on the bottom right, different slices, and they use it as input to drive the large eddy simulation. And then they can see how it influences the forces that act on the wind in tall buildings and similar things. Another application I would like to emphasize is just because right now we've seen our rather simple domains, you can have those random fields on very complicated domains. This is the brain surface. It's work from Lincoln and co-workers. So also here you can see the random structure on site on this seemingly random manifold, which is the brain. All right. Let me briefly give you an overview of the talk. So we just discussed point one on random fields. I hope you saw that it has many applications and it can be very interesting. What we want to do now is we want to tackle fractional PDEs in point 2 and stochastic PDEs in point 3. We do that because in point 4, we want to solve a PDE, the SPDE, coming from the SPD method, which needs both the fractional components and the stochastic components. We specifically address those 3 points in the context of finite elements and especially MFEM. And in the 5th point, we want to tie the random fields to topology optimization. So but let's move to the fractional PDEs. Fractional PDEs it's a wonderful field. It's a deep field. There's a lot of theory that we could cite here, that we could emphasize here, but we want to keep it super basic. So we want to stick with the fractional Laplacian and the Laplace equation for the fractional operator. Before starting, I would like to explain you why we actually think about those things if we talk about random fields. And the reason is that the fractional exponent that you can already see in the example, the alpha divided by 2, this one kind of like ties to the regularity and smoothness of the random field. And if we didn't have the fractional exponent, we could also only have like applying the Laplacian once or twice or 3 times. So it's kind of like discrete. But with the fractional power, we can continuously modify the regularity of our field. All right, let's go to the example. So it's the regular Laplace problem, but we have this fractional exponent. The fractional exponent alpha is bound by 0 and 2, and we employ homogeneous Dirichlet boundary conditions. When I first saw this equation, I felt like it's super interesting, but I have no concept whatsoever it means to apply the Laplacian to the power of 0.0243. I didn't know it, but there's a definition that takes care of that, and so I would like to give it to you. there is actually a bunch of different definitions that should be emphasized as well. And each of those definitions will lead to a different solution, numerical solution. But since we agree on a common definition for this talk, it should be fairly easy for us. So we use the spectral definition. And the spectral definition is kind of coming from spectral theory, where we say, okay, we have the Laplacian, and we can define its eigensystem. So that would be its eigenfunctions and eigenvalues. And then in the second line, in the second equation that you see in that box, we can define the action of the Laplacian onto a function u in terms of its eigensystem. And when we now want to generalize this definition to the fractional Laplacian, we simply introduce the exponent for the Laplacian and the same exponent we get for the eigenvalues. And now we have to find our fractional Laplacian, and it's a rather straightforward definition. From here on, we could now start proving things, but that's not what we're going to do. We would like to build some intuition such that we better understand the problem. All right, here you see the solutions for different alphas. In blue, we have the reference for alpha is equal to 0. In the curved red line is alpha equal to 2. So these are kind of like the two classical problems in our problem setup. And then in between, we see the different green lines. These are coming from alpha equal to 0.1, 0.5, 1.0, and 1.5 from top to bottom. You can see it's like kind of like continuously deforming. And if I had to ever write down a definition for a fractional Laplacian, this is what I would like to see. I would like to, if my values are between 0 and 2, I would like my solutions to be in between as well. So I think this is the intuition that you should have. Admittedly, it's quite an easy example. It's 1D. We can make that significantly more challenging by going to an L-shaped domain with MFEM, and we solve it for different alpha. So this one is example 33. It's part of the 4.5 release. It has been mentioned before. I invite you to play around with it, and you can replicate those results quite easily. The black box at the bottom tells you how to. So what you see here is different solutions for different alphas. We go from 0.2 on the left to 2.0, which is the classical Laplace problem on the right-hand side. And you see that the solution is getting from rather bulky to rather pointy, which is probably not the best way to describe it, but I think it does the job. And what you should see from that is that it gives you really some additional parameter to model something. It's like an additional thing that you can tweak to best describe your system. And that's interesting. And that's also why it sees so many applications nowadays. I've showed you how that these fractional Laplacian exist. I've shown you the solutions to it. But what I have omitted so far is how do we actually get the solution? And this is done by a method called rational approximation. And I would like to briefly explain that. So really briefly. So in a nutshell, we start off with our equation and we move the operator to the left at the right-hand side by simply applying its inverse. And then we sort of make this change. We say, well, let's replace the Laplacian by x first. And then we would end up with x to the minus alpha instead of minus Laplace to the power of minus alpha. And this function, x to the minus alpha, we can approximate with a rational approximation. You can think of it like a Taylor expansion, just with different terms and slightly different properties, but the idea is very similar. You have terms that with increasing accuracy approximate this function. The nice thing is that this approximation carries over to the operator due to central results from spectral theory for normal operators. So we can apply the same logic to our Laplacian operator. The coefficient itself, we get it by the AAA algorithm, but there's alternatives. The key point that I would like to emphasize is that if we now plug the second box into the first one and slightly rearrange the equations, we can see that it's equivalent to solving the fractional problem. It's equivalent to solving n reaction diffusion systems and add up their solutions. And kind of like the pitfall of this method is that we definitely need an efficient way to solve those equations. But since we have MFEM, we can do that. We have a very powerful tool to solve these equations, and therefore it's not a big problem for us. We solve these equations, we add them up, and we obtain our approximation to the fractional Laplace equation. This looks as follows. So on the left-hand side, you have the different reaction diffusion systems. We solve them and add them to the right-hand side as correction terms. Left, you see that the values are getting smaller and smaller and smaller. This is kind of the property of the series expansion, right? We have smaller and smaller values. And at some point, we almost converge, or the contributions get smaller and smaller. And this is kind of the logic behind how to treat the fractional Laplacian with the series expansion. So that was point one. We wanted to understand how to treat fractional PDEs. This is one way to do it. There's also a second thing that I would like to comment on, and this is stochastic PDEs. There's two ways to have stochasticity in your PDEs. Either you have it in the coefficients or you have it in the stochastic in the load. We only focus on the second point right now because this has been implemented in MFEM by now. What it means is that if you had a square domain, the thing that you can spinning on your screen right now, this could be the load of your system. And the question arises, how do we handle the stochastic load within a finite element context, but especially within MFEM? And both questions are answered on this slide. On the left-hand side, you see a paper from Croce et al. On the right-hand side, you see the pull request that finally introduced kind of the logic of the paper to the MFEM repository, done by Brendan Keith and Stochastic PDEs. So while I would recommend you to read the paper because it's really well written and very interesting, all you need to do is to get the stochastic right-hand side is the following. So the question is how to apply a stochastic load with MFEM. And the answer is super simple. It's 4 lines of code. So you start off by creating your linear form. You then get your integrator, your white Gaussian noise domain LF integrator. You add that domain integrator to the linear form, and then you assemble it. And that's all you need to do to treat your that stochastic load. It's very simple. If you had to get a second realization of that right-hand side, you would simply call b.assemble again, and you're done. All right, let's quickly pause here because now we've achieved the following. We have understood how to treat fractional and stochastic PDEs to some extent. And we can put it together in the following equation. And this is the equation that is kind of like the backbone of the SPDE method. We have an operator, it has a diffusive and a mass term, and we have this fractional exponent. And U is our solution. On the right-hand side, we have eta, which is like a normalization, and we have the white noise. When I first saw this equation, I thought this is going to be pretty ugly. But actually, now that we've understood those concepts, it's rather easy to handle them because we first use the rational approximation to break that equation into a system of PDEs that are independent of each other. And then we have the white noise integrator on the right-hand side, such that we can treat the stochasticity. We just put that together and we can solve this equation and get the solution. But why are we interested in the solution? So I call it the SPDE method, right? Well, not I call it the SPDE method, it is called the SPDE method. The central result here is I don't want to focus too much on the blue box on the left side. So we have a normalization constant. Yes, we've seen the equation. The domain can be arbitrary, the boundaries can be arbitrary. But what I would like to emphasize here is the theoretical results coming from the papers on the very bottom. So they state that the solution to this PDE is a Gaussian random field with Matérn covariance and zero mean. That's the two characteristics that each and every Gaussian random field has, right? The covariance and the zero mean. So it's completely defined. We have two parameters in that equation, which is nu and theta, and they define the smoothness or regularity and the spatial structure of those random fields. Awesome. So we've reached that point where we can generate those random fields, and I would like to give you a bunch of examples right now. So from left to right, we go from not smooth at all, nu is equal to 0.5, to rather smooth, nu is equal to 4.0. So you can see that it clearly varies. You can also see that they all look very much the same, but a bit more noisy on the left-hand side. This is because we use the same white noise for all these experiments right now. So we varied nu, but we can also vary theta. And for theta, we express it as a matrix. You can see the definition of theta on the top right of your screen right now. And if we vary the L1 and L2 inside that matrix, we can generate different correlation lengths, and the random fields start to look very different from each other. They're definitely different. So we go from very small correlation lengths to longer and longer correlation length, but also we can have them anisotropic. So like on the very right-hand side, you can now see that they behave differently in X and Y direction. All right, wonderful. I feel like I'm also running short on time like everybody here. But I would still like to try to tie it to the topology optimization. So we've seen topology optimization in the previous talk. Let me quickly recap with one sentence what it is. Topology optimization is a mathematical method that optimizes the material layout within a given design space, and it's subject to certain constraints like loads, boundary conditions, and other constraints. And the goal is always to maximize the performance of the system with some regard. So the image you can see right now in your screen is the computer's answer to the question, how do we distribute the material inside a square domain such that it extracts heat from a uniform from the domain in the best manner. Unfortunately, your computer doesn't speak my language, so you will have to define it in a different way. You have to use mathematics. And here it's quite clear. We have an objective function. It states that we want to optimize the thermal compliance. And then we have those different equations next to the subject too. So the first equation set tells you we have to respect the physics. This is linear diffusion for the heat. The second equation tells you, well, actually this is filtering to ensure the existence of the solution. Then the third one tells you we only can use a limited amount of volume that I can distribute inside the domain. The fourth one is the density field between 0 and 1. So we have either material or no material. And the fifth one is the solid isotropic material penalization. It means that we want to find sharp transitions because we cannot produce a 0.5 material, but we can only have like zeros and ones, right? Material and no material. So this one is a penalization term. We also have boundary conditions. In that case, we have homogeneous Neumann boundary conditions on some part of the domain, and we have inhomogeneous Dirichlet conditions on a different part of the domain. If we now run the optimization, the optimizer iteratively finds better and better solutions to this problem and optimizes the topology of it and finds this kind of shape that we've just seen. All right, but so far no random fields. So where do those random fields become useful? And the point is that if we find a design, like for instance here, it's a slightly different problem, but ultimately the logic still applies. The colored full image is the result of the topology optimization. The blueprint is kind of like the device that we want to build. By adding random fields or by using the random fields as threshold, we can generate different realizations. We can see that it might be problematic. Those realizations take into account the uncertainties from the manufacturing process. But if you take a look at the top left realization or the bottom left realization, you can see that the manufacturing process, in this case modeled by the random field, kills some of those connections. And then obviously the structure will not hold up any longer. And so what we have to do is we have to include the random field inside the optimization loop, which leads us to topology and optimization under uncertainty. And I'm almost done, my last slide. So what this means is that usually you have some filtering that leads to a design, then you apply some thresholding and it leads to the middle design, but the design might not be as appropriate as before. And what we need to do is we need to include the fields inside the topology optimizations. I was about to close make my last comment. So the point that I want to make is if we include the random fields inside the optimization loop, the optimization procedure adapts to the uncertainties in the system and can find structures that are manufacturable in contrast to the middle one, which is not. And then we find structures that we can produce and still have this optimality constraint that we lose from going from the first image to the second image. And with that, I would actually like to end the talk. I think the random fields have very good applications. We've seen that we can generate them with MFEM and fit it into the entire MFEM ecosystem. So with that, I come to an end.